thanks for not suggesting that, because I wasn't going to, because we didn't have any time. But then I sort of had this other thought, well, I could just do a sort of whiteboard type thing and say lots of random stuff, try and put together a big picture, because you're all very bright, and then if you think it's wrong, you'll be able to say. But I did think it's kind of maybe like preaching to the choir, you know. So, if you disagree, then say so. If you don't disagree, then just sing back. You know, that's fine. So I think this is probably quite maybe it was a useful quote, but now I get irritated by this quote because it's become a sort of excuse as to why your model is wrong. So people sort of say this, and then they say, oh, that's why my model is wrong, because all models are wrong and some are useful. The implication being that because my model is wrong, it might be useful. I think that's a bad way to start doing modeling, and I think it comes from history. Maybe that's true, that quote should be true for traditional statistics, but I'd like to argue that that's a very limiting way to think. So let's write down data, and then we write down data y, and I've written data y is in, so I like using these design matrices from statistics. So there's n data points and there's p dimensions. That is wrong. As soon as you've written that, you've written something that is wrong. And we should not do it. Well, we should do it, but we should accept that when we're doing it, we're starting to make modeling assumptions. And so I sort of want to, well, I wrote this little thing down. Why is it wrong? Well, everyone talks about large p small n problems, and they come from writing matrices in that form. But I sort of think worrying about large p small n is like worrying about runaway inflation in the Weimar Republic. It is a problem of the 1930s statistics, not modern statistics. The right way of writing down data is small y, where y is a vector, is in n by 1. Everything you know about the world is just an observation. And this vector is just the instantiation of what we know. Of course, it gets indexed by many, many different things. So this is just a particular way of writing down one of the indices. It's like saying, well, I've observed p things about an object, so one of those indices, I've dropped a pen top, one of those indices is the things I observed, like the identity of researchers in this room, or actually Philip at the Gaussian process winter school gave a nice example, like the identity of different types of sandwich I might be interested in eating, so a tuna sandwich or a burger. So, you know, this might be the sort of price of tuna and burgers across some different times and spaces. So each row is a different time, so we're looking at how things evolve in time, and then these might be tunas and burgers. But of course, if we say we've got a matrix like this, what happens if someone inventions a club sandwich? You know, we've already restricted ourselves to some sort of p, and then we keep on making these assumptions about p as if it doesn't move. That's wrong. The big data streaming modern world, we get pieces of information, and each thing is an individual piece of information, and it just has an identity. So it has an identity like, this could be, this is a real, so I've written n by 1, but actually, of course, I think that this could be indexed continuously. So this could be indexed by time, it could be indexed by location, it could be indexed by type of sandwich, so I'll call that I. It can be indexed however we like. It's just a very, very long vector of things that happen in the world. So the first point I'd like to make is that the way to deal with large p small n is to point out that p doesn't exist. And then you don't have a large p small n problem, okay? So I'll come back to that in a moment. It's so p is really merely another way of writing n. That's all. Okay, so this is a quote from Peter McCulloch that actually Peter Diggle's given in a couple of workshops that I kind of like. So the answer to any prediction problem is a probability distribution. And I think probably in this room no one disagrees with that quote, but that's by Peter McCulloch FRS, so that's proof by intimidation. If I say it, then it doesn't mean anything. So I'm just going to subscribe to that, and I'm going to say what we want to do, and I think most people here would agree, is we want to model y, probability distribution over y. So what I'm arguing is this model is correct. Yeah? No one can disagree with that model. What model? Very good. What model? Precisely. So, by the way, I'm trying to. So there's a spectrum of things I'm going to say. So correctness also applies to what I'll say, perhaps. So there's a whole spectrum of things you can say that are either interesting or correct. Now, I'm going to err on the side of interesting when I do err, okay? So just be aware of that. So what model? Precisely, Dan says. But it's not wrong, is it? It's just not interesting because it's not useful. But starting down by writing, oh, this is like this, has already made a modeling assumption, in effect, implicitly, before you even start. And what we should think about is starting with that. And then we've not made any assumptions. But what can we say about it that this must satisfy? What can we say additionally over, that's the graph of P of Y? So I think number one is we have to have Kolmogorov consistency in this model. Because this isn't just a model, this is a process model. It's not just the model of things we've observed in training, it's got to be the joint model of all things we observe in the future. So Kolmogorov consistency, I have not read the entire proofs and everything else, but I just summarize it like this. That's true regardless of the cardinality of Y star. So it doesn't matter how many future Y star things there are going to be, how many things we're going to see in the future, this has to be true. Yeah? So it's a condition on this modeling framework. Whatever modeling framework we do, in order for it to be not wrong at the outset, writing down, this has to be true. Now, any comments on that? Yeah?
This is one of the reasons I don't like Markov logic networks, not that maybe anybody here cares, but they're sort of frameworks for defining relations over data in terms of a big Markov network, but they just don't satisfy that as far as...
So anything that doesn't satisfy that is problematic. So another sort of thing that I do quite like, I also don't like Markov logic networks, but for reasons more irrational than Zubin. So if we've got data like this, and we're trying to use a some sort of restricted Boltzmann machine model to model our data, then we need to include Y star. So I like the idea of so I don't know much about Zubin's mum, but I know she doesn't like it when you wear a rucksack. But I don't know whether she has ever driven a Range Rover. And I wondered if I found out Zubin's mum drove a Range Rover, would it make me think something different about Zubin? I would think, oh, well, maybe she lived in the countryside or anything like this. But Zubin might just mention that in conversation. And now I've sort of made that up as an example so I can model it. That could be whether Zubin's mum drives a Range Rover. But he could say anything about his mum that I haven't considered. And that's an additional Y star here. Now the problem is, in say a restricted Boltzmann machine setup, where these things are all connected together, if you have this additional P, then when you have that additional P that Zubin mentions just in passing, that I didn't realize he was going to mention, I have to ensure that this model stays consistent over that, and this model doesn't stay consistent. So this model becomes a different class of models. So you can immediately see that sort of these very discrete models are problematic in this sense, that they don't fulfill. These models are wrong already. So Zubin used the example of Markov logic networks. I mean, we can use many examples. All models are wrong, apparently. But you can see right from the start that there's a problem with this type of framework, and I think we should always consider that. And this type of framework considers this sort of thing. The reason it sort of works in practice is P is fixed. And the sort of things that they've been very successful, well, people use them for modeling images, or if we look at a neural network type approach, the reverse approach, then they work just fine, because P is fixed, and that's not too restricted assumption, even though it's wrong in general.
Can I say something? Like, I'm not so bothered by models being wrong, but I am bothered by models being incoherent. You know what I mean? It's okay to be wrong, I think, but it's not okay to be incoherent.
Yeah, so what I'm trying to do, I'd agree with that.
Sense of wrong.
I'd agree with that.
You know, I could be wrong when I go into the casino and I miscalibrate my probabilities. That's perfectly okay. But, you know, at least, hopefully I'm satisfied with these rules.
So I think these models are interesting and useful. But I think what I'm trying to do at the moment is just sort of come up with things we can do once we've written down this that actually take us away early on, when there's actually other things we can do that don't take us away. And I think one problem is that we're kind of set in this era of data as a table. So the way we process data is we believe that it arrives in matrices Y, and then if there's several matrices Y, we call it multitask, or something like that. And then we sort of think that that's all structured, and then I assimilate that using some sort of structured model, and I build in conditional independencies like of this type, and as Zubin said, it's quite right to do that if you know that's the case. But actually, I think with big data, and with sort of streaming data, and with like robots moving around the environment, the way humans deal with things, it's not like that at all. Someone tells me something random, and I have to assimilate it. And we need to be able to assimilate each of those pieces of information. And this is why I sort of say it's back to that 30s sort of view of statistics, is because our perspective on these things comes from there. When people really, that's how data sets were collected, they were tables. Statistics was about, you know, understanding tables of numbers, which is like that. Okay, so there's an example, this made example, which I like, that Tonio Hayden quoted, that it's from Michael Goldstein originally, of that you're doing your inference on, in a trial, and you're just about to declare guilt or innocence. And just as you're about to declare it, a maid runs in and says he's not guilty. What do you do to your belief of guilt? And the point about the thing is you didn't know the maid existed before you started. So if you were going to change your belief in his guilt, my odd answer at the time, a few years ago, was you do nothing because it wasn't in your model. And anyway, you're not allowed to introduce a witness at the last minute. So it seems to be about it. But you know, the point's the same. That you can't, if you do listen to the maid and think, oh, he's more likely to be guilty, then every time the maid doesn't run in future, you have to think, oh, he's less likely to be guilty. And the question is, are all the possible things that can happen, like butlers and gardeners and everyone else turning up, if you sum over all the things that could happen, does that change your set of beliefs? And that's this property. So you need a model for which that's true, that, or else it's not consistent. You smile. Why are you smiling? That's like the idea of the maid.
I went to visit somebody the other day, and we were going to have a conversation with them, and they locked the door. Right, that doesn't happen very often, right? But you can sort of see now that there might be a motivation for doing it.
Yeah. They didn't have models that obeyed confidence. Well, to be fair, across the whole universe, it does. I suppose if it's a finite universe, it doesn't. But you know, let's assume that there's so many things that we can't observe that it comes to the same thing. So I think that means. So I'd say that model it should be non-parametric. You know, other people have said this before, including I think Zubin's got this in a paper with Ian. You don't want this information bottleneck. So if you're going to talk about your test data, given your training data, another condition, which I think is a separate condition from this, because you can have this condition. Another condition is that if you have a parametric model, so if you decide early on to put in some sort of set of parameters and make some conditional independent assumption, I'm going to draw that in a minute, so I won't draw that now. If you decide that early on, to do this, there's your likelihood, and then you have a posterior over, let's call the parameters theta, makes it a little more technical, comma, let's not even put the index on, just y, so that's our training data. If you decide early on to parameterize things and set them up like this, what you've done is at design time, you've specified a fixed dimensional vector. So this is before you've seen the data, you're making a very, very strong assumption. It may be correct and it may be usable, but at design time, you're putting in, I call it an information bottleneck, and I don't know, I was trying to think of it, maybe Zubin, you already had a catchy name for that, but I thought of it as the TT channel. This is like an information channel between the training and the test data. So the TT channel is sort of finite bandwidth. So, and you're doing that before you've even started really looking at data. It seems odd. So that seems like a bad idea. So it shouldn't just fulfill this, it should be non-parametric in the sense that theta should not be limited. In terms of, when you're having a conversation, when you're using this TT channel, the TT channel should respond to the amount of information that you saw in the actual world. Or should be adaptable so that it can respond, because that's going to prove problematic to make it respond. And that's when, hopefully I'm going to say something. I mean, I don't know, maybe some of this is new and some of it's not, I don't know. It's just what I think, and it's influenced by all sorts of other people and what they think, so it probably is identical to what other people think. But hopefully some of it will be things you haven't heard. Okay, so the principle, don't make decisions at design time that you will regret in operation, because that's going to ensure that your model's wrong. Yeah? If you make that out the front, And again, in practice, we have to maybe do this, but I'm just thinking about that statement. Okay, so yeah, think of that as the information bottleneck. So this is a little bit of an aside. When we did the big data workshop at NIPS, Zubin was talking about non-parametrics, and then he said that PCA was non-parametric, or something latent variable. What did you say was non-parametric? Matrix factorization was non-parametric. Yeah, I suppose in some sense it is. So, matrix factorization, I think the reason that can be non-parametric is because every time you look at a new user or item, you have to actually augment your parameter space in some way. There are other models that look like they might be non-parametric, like PCA, but it's sort of not, because although it has infinite parameters, those parameters aren't used for communicating between training and test. So, depending on how you set PCA up. But standard probabilistic PCA, where you sort of have an assumption that your Y is dependent on some latent variables, and those latent variables you have to marginalize out. That looks like it might be a non-parametric thing, because there's latent variables associated with every data point. But the way you set up the model is such that you get independence between training and test, so you end up with, the information is passed through the principal components, not through the non-parametric variables. So you have to be a bit careful. I also found out a lot last week, the term non-parametric can even be misleading. I don't think a lot of people don't, I don't want to say non-parametric almost anymore, because I want to say this, that this channel needs to respond to the data set size, and this. And I don't really know what, some people mean different things by non-parametric. People say, such and such a model is non-parametric, and you think, no, it's not, you're an idiot. And then you realize they're not an idiot, and then you realize they must have a slightly different definition of non-parametric. Okay, so just to add another thing to my little drawing over here, I was going to build on this drawing, but I sort of drawn around it. So I'm going to expand my model a little bit, because what I'm going to say that what often happens in the real world is while we observe F is related to some fundamentals of the real world that we actually care about. So I think that it's very reasonable, even if, so in the worst case, F becomes directly equivalent to Y. But in many cases, you're observing something that is obviously the sum of two other things. And you want to include that, and you can include that very often in factorization assumptions about how, so all you're doing now is saying P of Y given F, P of F, integral over F. Of course, that's just the same, it's just a joint model. There's nothing unusual going on here until we specify something about these things. We're not specifying sparse connectivity or anything else. But we might like to, and I think without loss of generality, we can think that P of Y given F might be factorized in some form. Not necessarily independent, but although I'll play with totally independent across Y. Even if it were totally independent across Y, if it was deterministic and independent, it just comes to the same thing. So you've got some sort of independence across subsets of Y, which I'll indicate like that. But it could depend on the whole of F. So we don't observe necessarily F directly in the real world. We often observe Y. So F is some sort of fundamentals, and actually we can model here without worrying about that, and that transformation is just to make things simpler. This could include non-linearities, the sort of things that we're copular models, that sort of thing, the sort of things lots of people care about. So I don't think that changes anything. But then another thing that is perhaps people don't normally think about is look how many graphs I can draw that don't say anything. Is the hat. So U. Now why am I drawing U? Well, I want to sort of colour these in a little bit. This is like a picture of the world. So this is South America, this is Africa, blah, blah, blah. That's what's going on in the world. This is like the physics of what we think is going on. Perhaps maybe we put some understanding about, how do we get things over this? I think the difficulty is that what we really want this to be is just mathematical truth. But there's very few laws we can get from mathematical truth. One of them is law of large numbers, which actually leads to increasing entropy. So the underlying laws of physics, conservation of energy is just an empirical observation, but increasing entropy is a consequence of the law of large numbers and the way things behave statistically when they interact. So I think that's why maximum entropy is perhaps quite a general principle, although that's a looser sort of connection. But ideally, that would be that type of law, that it's driven from the law of large numbers. It could also be driven from things like, so some people, there are sometimes modelling assumptions which do not which cannot be sort of picked out as incorrect given your model. So an example is a pollen on top of some water bouncing around in Brownian motion, yeah? So the model for what's going on here is that this thing is being impacted in finite time by a infinitesimal amount of time by a water molecule that bounces off and then goes off somewhere else, and then with finite energy. So this is being driven by a white noise process with finite energy. None of that makes any sense. It can't physically exist. So what's really going on is very much if you did like dynamics at university, you often had these impulse functions of infinite height and finite size. And you look at a differential equation as responding to this type of impulse. That also can't happen. What's really going on is when you hit it with a hammer, there's some sort of finite width. But the time constants of the system in both these cases are such that the real system is not identifiable, given the data, from the system, the abstraction you've made. So the abstraction here, that this is driven by white noise, or the abstraction here, that this is driven by a delta function, you can't identify the difference between the truth and your system, given very often the data set you have. So that's an interestingly odd thing, that some models, you know, if you can't identify these parameters, you almost, it's not Bayesian, I don't think it's Bayesian marginalization, it's something different, and I haven't quite understood what it is. But it's an abstraction, and it's used in multi-scale modeling all the time. So when we model at different scales, what's really going on in the air is what air molecules hitting each other sort of somewhat deterministically. But we summarize what's going on in the air with a Gaussian density and temperature and pressure. So with these sort of sufficient statistics of the Gaussian density of what's going on in the air, just by its variance, independent variance. And that's all we need to do like loads of computations. For an ideal gas, it's perfect. And a lot of modelling should perhaps be done like that. Be thinking about the basic principles and what can we identify given. But it's not, I don't really understand how that fits into Bayesian marginalization. So that's one sort of idea of how we could try and model fundamentals. You know, I've worked in that sort of direction. I'm not saying in any shape or form perfectly. But there's a problem that non-parametrics requires infinite parameters, in effect. So what is U? Well, U is U. U is what you're going to store about the world in order to summarize what's going on about Y. Now, this is still meaningless because we haven't done anything further yet. But by including this explicitly in the model, it's an important point, and making sure that Kolmogorov consistency applies for U as well as for Y, then it's going to be confusing when I say U now. You can ensure you can ensure that you get to change your model at runtime.
So, okay, let me think about this. I mean, your notation suggests very strongly a picture of the world that's where Y is the data, F is something like a Gaussian process maybe, and U is something like perhaps some inducing points, right? The funny thing is, F is infinite dimensional in a Gaussian process, but U is finite dimensional usually.
No. Yeah,
well,
that's the
question.
mistake.
That's the thing.
That's the mistake people
make. So then
make.
is it, yeah, so the question is, are you taking the Gaussian process and then making a parametric version of it?
Yeah, I think that this is, so I think a lot of this inducing variable stuff is like a 3-card trick. Where's the non-parametric model? There it is, there's the non-parametric model. I introduce inducing variables. Where's it gone? Where's the non-parametric And it's a little bit confusing, isn't it? There's a lot of non-parametric facets to these models. And I believe that they are, you can sort of show that, well, that's the point in the variational approximations. People keep writing about the perspective that Carl and Joachim gave in their paper. That perspective is dead. It's dead. It's a wrong-headed thinking approach. It was great. I was there. We did it. We were excited. You know, it was a workshop where it was all formulated. I totally believed it in the time. That perspective is wrong-headed because it has this type of side to it. I'll come back to that. But precisely, but back to your other point, why is U finite dimensional? Whoever said that? It's part of our modeling framework. It's not a condition, it's a parameter, so it's a variable alongside Y. Now, let's see where I am just in terms of when I was going to say the stuff that you're asking questions about. Yeah, so actually the next slide I was going to show, so we'll come back to that in a bit. But yeah, so I've said, so I've actually put these slides online, there's a PDF link to them. I finished them on the train and I photographed them, scanned and turned them into PDF and put them on my webpage, on my talks. So you can sort of see what I'm reading from. And my drawings, which are really good on here. So you need a representation of the world, U, that is finite dimensional, but is not a design time constraint. Because we're going to still apply homograph consistency to U. So we're allowed to suddenly instantiate new U's in response to what the world's done to us. And all we know, when we come to approximate, we're just improving our bound on the marginal likelihood. We're not changing the model. So the problem in the world of these finite things are outside the probabilistic framework, the old way. So sort of I've got some examples of traditional approaches, 1930s approaches. I think they're cool, you know. I like a lot of Art Deco and stuff like that. But I don't think we should think necessarily along these things now. So this is where we've got a vector of features, and then we have parameters like that. Now this leads to the large p small m problem, because these parameters, sort of p-dimensional, and if n is small, these parameters aren't well defined. It's a non-problem for a Bayesian because you marginalize over theta and you recover models that look like this. You should never have written it down like that. You should have written it down like that and then later made an assumption when you realized it was going to be all right. But you shouldn't. People say that cursive dimensionality, that's a modeling. I mean, curses of dimensionality do exist. But the way people bandy it about, like, my model doesn't work because of high-dimensional data, it's not my fault. No, it's your fault. You modeled it incorrectly. I mean, get a grip. This model here, you should not be applying it if P is large, obviously. So what do you do? Well, I had this paper, the GPLVM, and then at some point I realized what it was doing was this. Now, this is an odd model, according to, that's an index over J. So this is back to the sort of wrong starting position here. So this is now independent over columns of Y. Yeah? If we're going to be independent over columns of Y, this model leads to a large n small p problem. So that's absurd. It's a consequence of model definition. I mean, these parameters, they scale with n, so in some sense it's a little bit non-parametric, but we couldn't marginalize over them in the original model, so we were maximizing likelihood. And someone sort of pointed out, well, it's not consistent in the likelihood sense. Well, that doesn't worry me because I don't really worry about getting infinite data any day soon. But then you suddenly realize, but it is consistent as your number of features increase to infinity and your data set size stays fixed. And then you think, well, the whole definition, it's just a matter of definition. There's these nice examples Josh Tannenbaum uses of sort of animals with certain characteristics. Well, we sort of think, well, imagine if you've got your data, you've been asked to model some data, an ecologist has been out in the wild and he's been looking at birds and saying that they have wings, and you know, then you look at fish and say they don't have wings, but that they go in water. So he's got this data, and it's great. You're sitting there modeling the data across this. N is the number of organisms he's looked at, and then you're just about happy with your model, and then the ecologist comes in and says, great news, a really keen PhD student was just out there, and not only did they get the data we've already got, but he noted down whether or not these animals have scales. And you're like, oh, what an idiot. Now my parameters are less well determined, and I can't do my modeling as well as before. It's absurd. More information is always good. And the reason it's absurd is because when you write down that, you're kind of starting to make assumptions about factorization. That's the traditional one. That is the assumption underlying, so Zubin's work on semi-supervised learning with John Lafferty and Jerry Zhu. It's also work underlying a lot of Josh Tannenbaum's work about what models that sort of data. It underlies the GPLVM. And in a recent paper I showed that it underlies a lot of the spectral clustering spectral dimensionality reduction approaches, if you view them probabilistically, that they assume independence across P. And they work very well in high-dimensional data. So you have a choice, is the point about that bit. Even if you don't believe in this framework, think very carefully about how what your data is and how you want to declare independencies, because the cursive dimensionality is your fault. It's not the data's fault. You know, you have to stop blaming. I mean, maybe you can't fix it, maybe it's a difficult modeling thing to fix in that particular domain, but it's your fault, yeah? Not the data's fault. Because P doesn't exist. It's just how you chose to measure it. So, questions at that point? I don't know. I sometimes think, well, this is different to what people... If I taught this to like my master's students, then they would be really confused because all the textbooks say something different. So I think somehow it should be controversial, but no one ever complains about it. So that even means like I'm an idiot, and everyone's thinking, oh, he's gone so far beyond, we're just not even going to say. Which is absolutely possible. I do not have zero probability on that
it's a good basis.
point. Yeah. Lindley says, never put zero in something unless it's a logical impossibility. So
when I approach problems like this, I think about symmetries that must hold of my subjective knowledge. And so both of these models imply very strong independence, as you were just discussing. But like, say, in the case of what the model that you're talking about with Josh's, if you have mirror, say, you can think about the data as being birds are at the end, and then the feature, and then you're
all of a sudden this is this transpose. Yeah.
Yeah. So, but if you have mirror, say, array exchangeability, if you treat it as an exchangeable array, not a sequence of exchangeable rows or a sequence of exchangeable columns, then you get a richer parameter space, and you're not making these mistakes. Yeah, precisely.
You're sort of back over to this type of domain. It's the way I see it.
But I don't think this is a failure of maybe this is assuming too much in terms of symmetries that exist in the data. But you can
they might exist.
They might exist, but it might be too strong. You made an assumption a priori. But even array exchangeability might be too strong, right? I mean, it's often going to be too strong because it means that array exchangeability means that if that student came in and had written down scales, if before he handed you the data, he swapped the scale column with the scales with whether you were red, then that should not affect your inferences, right?
Right. So I is a sort of property of Y, and one thing I think we need to do at some point is be able to integrate over these things and do inference over what these things are as well, potentially, which we can do a little bit. And I think that's an example of what you're saying. You don't know what the identity of some of these things were, and that leads to some interesting effects. So I've sort of assumed we've got all those. But yeah, absolutely, you have uncertainty associated. I mean, so Y, I'm sort of almost saying, is a function of time, space, and a bunch of indices. Well, just summarizes I. And yeah, you could have problems with these, but I'm sort of neglecting to talk about that for a moment. But I agree, yeah, absolutely. And if you get those, then some of these assumptions will fall apart. Yeah.
I'm very sympathetic to what you're saying, and I also sort of agree with them that sometimes there's symmetries that you want your model to capture, and that kind of describes the sort of properties of the model that you want. But the whole concept of number of data points is very fishy, right? Like if you have one brain scan with 5 million voxels in it, is that one data point? Is that 5 million data points? Now if you have 5 brain scans of 2 patients, is that 5 data points? Is that 2 data points? Is that 5 million data points? So, all this stuff is very fishy. And
statistically they think about it. And I think that comes from these 2 domains, right? Because then they have interpretations. Number of data points now has an interpretation as a sample size and a sample-based approximation to minimizing some KL divergence. Yeah. And then it's meaningful. It's an independent thing, but it's a consequence of your model, not a consequence of the actual data.
Not the data.
And even if you do it this way around, the same thing, number of features.
Is the collected works of Shakespeare one data point, or, I don't have to belabor this, but, there is no concept of data points. So then when you look at statistical theory and you see something like, and then we penalize it by n over 2 log p, or something like that, it's actually devilishly hard to figure out what that n number of data
for a lot
points
of interesting
and p
models.
number of parameters should be.
Yeah, I think that's when I was trying to think about consistency, that's when that really, when you look at proofs of consistency, the simple ones I know about are all about minimizing a KL divergence sample-based approximation to the KL divergence, which exactly assumes that the samples are n, your data observations, and they've been independently sampled from some probability distribution. So a lot of that theory, well, in a way I understand only simple things. So I understand that simple proof. There's other proofs about consistency of models, which, but that theory that is associated with that proof is kind of only applicable for specific model sets, I think, as well. So I agree totally.
When you say model, do you include in that the decision as to does the model come after, say, symmetry conditions? Like, is a model for you also choosing between? Is choosing a model also choosing between these things? Is that part of the model?
No. Well, for the moment, maybe. I don't know. That's also a difficult thing, isn't it? Because people mean different things when they say model. So yeah, I don't know what I'm saying at the moment. All I'm saying is, how much can I say without saying anything? Because so far I've said nothing, apart from separating some things which have left us in that all models are wrong, some are useful, which I think that statement isn't true for. That actually, if you just write down this sort of stuff. Well, I think this condition, I mean, you're right, but, you know, I worry about, I'm sort of conditioning on index. Yeah, but you're right about the point about the symmetry.
So you mentioned earlier, like, what is F, and you were talking about this, that the data don't just help you distinguish between whether you're working with a Dirac distribution or a smooth function. In most of this, when you induce a symmetry, that usually by some kind of infinity like theorem induces a natural parameter space, and that parameter can always be recovered if you have enough data. That can always be recovered from, and with finite data you can recover well with high probability. It can always be recovered from the data itself. Often you see models that have non-identifiability, and that comes from making additional assumptions that go beyond the symmetries that you might have started with.
But I think that those need to be, and I think you need to make those, and I think they often come from physics. Physical understanding, I think smoothness really comes from physics. Everyone says, oh, why does everyone use the squared exponential, quadratic, whatever, covariance function? Well, it's got some interesting physics properties. It's actually the solution to the heat diffusion. If you've got point sources of heat and things diffuse over time, and you look at what the temperature is, then it's, it's that. And that, as we know, people talk about heat as if something flows. But heat doesn't flow, heat is a collision between a bunch of underlying molecules. So really, you're picking up some regularities of what happens when you get large numbers of things together. And then you're trying to put that in your model. And often I think that that's an additional assumption which might be wrong, but hopefully it's not identifiable at the level you're working at that it's wrong. As you get down to the molecular level, it's going to be wrong. But when you look at the PDE level in the room, it hopefully won't be wrong.
Because I think there's a problem here, which is you're talking about models without specifying what are you trying to achieve. Right? And that's why it doesn't really work.
Oh no, it does work, because I've just specified what I'm going to achieve. Because what I said, and it was Zubin's point, is this boy here. I do not want fixed parameters in my models. I'm trying to avoid this. And I'm trying to avoid this while storing only finite things. So I sort of think, so we've got a project where I don't know anything about it, but I would say that we're trying to claim in the project, the reason we're justifying using this in a sort of psychology-type robotics project is you as episodic memory. It's what your brain decides to store about the world around it. It doesn't store everything. But in general, you need that. I mean, whether it's the brain or whatever else, you need some finite disputed thing. I mean, I don't know anything about the brain, but clearly the brain did not decide at design time how much information you're going to see in your life. I mean, maybe it just used an enormous model and was fixed in parameters and didn't start using those parameters, integrates over those parameters, waits to update those parameters when enough information comes in. It could do that. But wouldn't it be more efficient if it can change its parameter space? If it's got this sort of exchangeability stuff going on over U? And that's what's going on. I mean, that's the next bit. That's what's going on in these variational approximations to Gaussian processes. And people aren't understanding because it's just a fixed basis. No, it isn't. It's a variational parameter. And you can add as many as you like at any time. And you can have them observe anything. They could be observing the gradient of the function. They could observe the integral of the function. You know, any linear operating light could be involved with the spectrum of the function. You've got your imagination. Is all that. So what you've got to define. I mean, I'm basically on the next bit.
But hang on a second. So if you're trying to achieve something, like say you want to cross the road.
Yeah.
Okay. You've got a model of how the world works, right? And at some point you're going to walk across the road. Right? Okay. Now, is that model correct? No, because there's certain, you don't understand everything about the world.
No.
So, is it a good model? Well, that's a meaningful question, right?
In theory, if I haven't said anything about the modelling framework. Until I say this is Gaussian, if you have the right distribution of how these things interrelate.
I don't think that's the right answer. But, I mean, you're trying to get across the road.
I'm not trying to say
all this stuff is irrelevant, right?
No, I'm not trying to say the right answer. What I'm trying to say is I'm trying to avoid wrong-headed thinking, which is actually a historical side effect of the way statistics used to work. And you know, I'm not saying, in fact, I haven't really said anything. I purposefully didn't really say anything up to this point, apart from we need a mechanism, and no one else I think is really sort of saying this, where the variables you're going to store about this sort of thing are jointly non-parametric with what you observe about the world. That's all I'm saying up to this point. So all this argument has just been to get into the point that whatever your model is, I haven't said anything about the model, so how we cross the road or whatever else, you know, I don't want to think about a specific circumstance, because then I have to start thinking about specifying the prior, well, I'm going to now. But up till now I haven't. All I've said is, you've got to have the ability to decide. So in these models, you get exactly this thing going on between training and test. But you can choose to be however big you like, whenever you like. And I think that's a really powerful thing. Yeah? I don't know. It's certainly a powerful thing in Gaussian processes. I don't know if it's a powerful thing in other non-parametric models, because I don't work with those models, and I don't know whether these type of ideas work. But it strikes me that it could be. I don't know. So you can't say I'm saying nothing when I admit I'm saying nothing. Unless you disagree with the last point. Yeah?
Well, I mean, I guess the question is, what's a model for? Okay, that's the question that Carl is asking.
Well, but then I haven't got to that bit, so the next bit I'm going to do is specify how you do this in Gaussian processes, okay?
So let's say you had the right model.
Well, no, I'm not. I'm just trying to. I think this is just. I'm just trying to kill this statement. I mean, model means an enormous amount of different things, and this model here said everything in the world could possibly interrelate to everything else in some way that I don't know about, and that is a much more. The problem with what this applies to, this statement evolves from this era. And I don't think it's satisfactory to sort of sit in that era and say, well, all models are wrong, so I'll give up. You know, maybe we can't make the right model, but we can't. I don't think we should be stuck with the problems of those models.
Can I paraphrase something that you're saying? So regardless of what models are used for, which is I think a very interesting, important question. If you're going to do modeling, you've argued for non-parametric models first, and then you've argued for computational methods or inference methods that are also that also grow in complexity.
Can grow if you need.
Can grow in complexity.
You can apply a trade-off, yeah.
In a coherent way, so that you're not just saying, oh, I'm going to do a non-parametric model, but I'm approximating with this finite parametric truncation, and that's it. And if I add a new parameter, then it's incoherent with what I did before. So that's the sort of philosophy you're going for, which sounds very appealing.
Yeah, that's exactly what I'm trying to say. But I think, back to Carl's point about modelling a specific situation, I should name the situation that inspired me to think about these models, and that is clinical data. So we have a number of patients, and we're getting information about patients. Why? And this information is labelled in all sorts of different ways, where the patient lives, what time this information came in, what this clinical measurement is. Now, if you think about that type of data, it can never be sort of drawn in this way unless someone is, at the outset says, we'll only consider this range of clinical tests. Now, if we're going to build a model over 39 million UK patients, which is capable of dealing with in clinical tests that doctors haven't even invented yet, then each of those has to be viewed in this type of way. You can't deal with it because otherwise you're marginalising out the existence of something you don't know about. Someone invents it. And it relates to some underlying phenomena, which is disease. Perhaps very weakly. But basically it's there. I mean, back to your point earlier, Dan, about when these things can go wrong. One of the ways in which things can go wrong is perhaps as you start marginalising over y's, where y's are sort of non-Gaussian. I don't know, well, not so much marginalising, sorry, not marginalising over y's, where they're non-Gaussian, where y is not missing at random. This is a very interesting one. When y is not missing at random, this model makes everything trivial when y is missing at random. But when y is not missing at random, an example is if you haven't had your cholesterol measured, you're less likely to have a heart attack than if you have had your cholesterol measured. Because
don't measure your cholesterol.
Yeah, so don't measure it. Absolutely, that's the correct.
Whatever you do.
Don't measure your cholesterol. So people say, oh, how do we deal with that? How do we deal with that? Well, actually, I don't think it's that complicated. It's not missing data, it's data. I mean, it's just weakly informative data. And that's why you sort of often have to have this separation. Because that's less informative about you're likely to have a heart attack than if we just randomly measured cholesterol in people. That would be more informative. And that can also lead to the sort of situations Dan was describing, I think, where you've got these weird sort of missing things that mess everything up, cause correlations that we won't. So in clinical data, I think that this sort of situation is very true. So now we're going to set up this model that's going to run across the entire country, and it's going to need to be adaptable at runtime. So we're going to get new measurements in. We need to update our ideas of what's happened, what patient's disease state is. We're going to get new diseases in, which are related to existing diseases. And we have to be able to incorporate all this. Dan.
So in my mind, there seems to be an alternative view on this, and maybe in practice this just doesn't work. But you could have the nominal model, which is just f and y, and then you could view u as part of the computational procedure. And as new data arises, and you deem through some tests that the size of the u that you're working with is insufficient, you can kind of develop computational methods with, like, say, frequentist proofs or whatever, for like how you can introduce more u's or reconfigure the u's, and then continue to do approximate Bayesian inference, but in this nominal model of f and y.
No, I agree. And if people work out a way of doing that, then I would think that would be great. I mean,
so it's just a matter of that's not understood how to do that?
I don't know what. I'm only worrying about what the bottom side work with. I don't think people in general know how to increase model size. I mean,
no, the model says f and y are the same dimension. That's just non-parametric.
Yeah.
But I guess my perspective has always been that u is about doing approximate inference of these models.
I'm nervous that I'm not going to move on to the actual technical bit.
All right.
I've got like 6 pages.
Well, I'll
but we have another question there. Yeah.
So I think in the abstract you also mentioned that you're going to change a bit the historical order for how that model was developed. And if you actually look at the historical order of how that model was developed, then basically you have f, you have y, you have too much time complexity to actually calculate y from f directly is too high, therefore you need to introduce u. If you just cap u and if you are willing to sacrifice time complexity in order to calculate y directly from f, how does that fit into this interpretation?
Don't know. I think that what I wanted to get onto actually is trying to say, at the end I'll say something about what I think is wrong-headed about, and lots of people seem to think, which I found sort of surprising, which is why I want to sort of give the message. But I need to do that. I need to start introducing real modelling assumptions. So, let me do that. So, I'm just nervous of time now. Sorry to push on. So, what we want to do is we introduce some modelling assumptions, and Gaussian processes are very general modelling assumptions. They're so general that under this thing I said before about abstraction of data, if you choose to observe your data in long enough time intervals, everything will hopefully revert to a Gaussian process. Even stock markets, if you view them over periods of 100 years, when lots of large events happen together, hopefully they might revert to Gaussian processes. So they're quite general. Obviously it's a modelling assumption. There's lots of problems. I work on those problems too. But it's the sort of, if we're going to instantiate a model, it's one of the most general we can do. So what we're saying is basically something like this. And this is also giving us the relationship between... now James, my postdoc, sometimes says, I don't know why Neil likes using u. Why doesn't he just use some other notation? I don't know. Well, very importantly, KUF is not necessarily from the same covariance function as KF. It could be very general. It's a variational parameter. We pointed out in a widely ignored paper called Variational Inducing Kernels, which said you can make any choice on KUF to say something you want to say about your data if it feels compressive. So the sort of choices you might make, as we talked about earlier, are sort of derivative observations. So what this model really tries to do is it says, well, I've got some data function here, and this sort of part of the presentation is based very much on my postdoc's James Hensman's approach to presenting this. I want to credit him. Not so much the fact that you can vary, because he just presents it as what he said is, okay, by putting in some inducing variables u, what these things are, if they live in the same space as f, they're observations about the function that I decide, I can design where they are. How we do that is kind of an open question, the best way of doing that. But what I'm also saying is I could also make statements about what I expect the integral to be in a certain region, if I found that useful. What would be really cool would be to optimize over what is the right thing to store. In theory, we can, because we know we're just doing that. Doesn't give us a worse fitting model. It just is a variational parameter. It just gives us a tighter bound on the likelihood. And we can even, there are even measures that show us when that bound is starting to approach the true likelihood in this setup, which is, the setup I'm really talking about is because Titsias's variational interpretations of sparse Gaussian processes. Sparse Gaussian processes is a terrible word. We should never have called it that. They're really low-rank approximations to Gaussian processes. So, what goes on in the maths? Well, we've now got these three variables, and we have p of y, comma f, comma u, equals p of y given f. This is our relationship between the fundamentals and the data. Often we assume it's factorized, but actually that assumption, some factorization I think may be necessary, but it doesn't have to fully factorize. And I think that assumption isn't too restrictive. The probability of f given u can be written down as, this is just like the standard Gaussian process prediction of a function given some observations, only now the observations aren't observations. And thinking about things in this way is, I think, really how Ed Snelson, working with Zubin, came up with some of the ideas for this sort of model. So the original way of thinking about these types of models was to write something like this down, and people are here who are part of that thinking, so they can correct me if I'm wrong, but I was also there. So perceptions change with time, was to sort of, let's try and do a parametric Gaussian process. So if we write that down and we have these bunch of u's, so if we have a prior over u's, if I just do the prior over u's as the same, well, there is implicitly a sort of prior. If I use it there, then I just recover the original Gaussian process. But if I make an independence assumption over p of f given u, or I can assume that there's certain sort of, I can assume other things, I get to different types of approximation. And the problem we had, I think, the big mistake, the wrong-headed way of thinking, was those approximations, they arise at these low-rank approaches, which when people said that that's the model. So they had these parameters in the model, as part of the model. They were model parameters, not variational parameters. And I think what Michaelis's reinterpretation really allows us to do is a lot more powerful. So that's the decomposition. This doesn't say anything about, I'm still not saying anything about things apart from their adjoint Gaussian process. Of course, I think most of the conversation of the Gaussian process winter school were about how you choose covariance functions. Massive challenge. These sort of things Dan was talking about earlier, lots of different ways of choosing covariance functions. I'm not saying anything about that, I've just written KFF for the moment. And the idea is that you basically want to store the posterior of u, given what's in the world. So you store things in a probability distribution, just like as if it was a parametric model. It looks very similar to a parametric model. But now we're storing things about these inducing variables rather than something like about parameters. But we can't do that exactly because this requires, so computing this, p of y given u, requires very often to invert KFF. And KFF is the same, I'm assuming that's the same size as all the data. So as we observe all the data in the world, this is just not going to be practical. 39 million patients and potentially, hundreds of measurements per patient. We're not going to be able to invert this type of covariance function. Okay, so what we do is as follows. So we can write down log, and this is sort of perspective James and I came up with, which is not how it's written in the literature so much, but I think it's informative. So you can write, this is just true. Now, if we take expectations of both of these under P of f given u, that doesn't affect, this is the standard sort of variational trick, that doesn't affect this guy because it's just an integral over something that doesn't depend on f. But what we get is this expectation, and I use these angle brackets for expectation, P of y given f, P of f given u. And then this thing here becomes the KL divergence. And this is informative too. So I don't think we understood this properly. I worked a lot with Michalis on this original model. He was at Manchester at the time and talked a lot about the sort of things Carl and Zubin had done. And I don't think Michalis and I understood the model in this way. But it's a much better way of understanding the model because the bound is introduced in a totally different way. What you're saying is, and this is really informative on that model we had before, is what I want to happen is my information, this seems to be the right KL divergence to minimize. My information about f, which should really come from y and u, I want to minimize the KL divergence between f given y comma u and f given u. So this is the extra information you get by knowing y. So in other words, we're trying to describe these functions by knowing u, but actually that may not be sufficient to describe the functions. You may get more information by knowing why your derivative observations of those functions as well. But very often, this KL divergence, if you have a well-chosen set of u about your perspective on the world, this KL divergence would be small. And I mean, to be fair, I've not actually introduced a Gaussian process in that proof. So things now work computationally for Gaussian processes, but if all these exchangeable things are true, what I'm saying here is true for sort of a family of models that fulfill those criteria. So I'm not really making modeling choices, I'm just pointing out something. That you can store, if you can get your model in such a way that you're trying to, if you try and maximize now, this turns out to be tractable. Because this is the expectation of f given u. Okay, I probably have to make some factorization assumptions about y and f here, right? Because I'm assuming that each y doesn't tell me about the whole of f. If that were true, I think I'd be in trouble. But if I think each y is telling me about a little bit of f, this thing is tractable. Because, and it's sort of in some sense easy to see, because this is the log of if it's Gaussian. If it's Gaussian, it's tractable. So I'm back to now assuming Gaussian. It's true in general, but it's tractable if it's Gaussian. Because this is the log of a Gaussian, so f appears in here as the mean and the variance, and those expectations under P of f given u are simply that and that. Yeah? So what you end up with is this nice approximate form, which I think is really worth thinking about and looking at, because it's very interpretable what's going on. So you end up that log, if you drop that KL divergence, sorry, I wasn't clear about that, so what we're going to do is going to drop this KL divergence, and we're going to look at still maximizing this quantity or some expectation of this quantity, which is, so if the KL divergence is 0, everything's exact, but in practice the KL divergence isn't 0, and what we get is that...
Can I ask a question? Sorry. I was just kind of, I was just going through, so the first equation there, it holds because y given f is the same as y given f and u.
Yeah.
Right. So the thing on the top, and then then you can, so it holds for any f.
Sorry, yeah, this holds for any f and any y and any u. This doesn't make any conditions.
Except that it has to be that y given f is the same as y given f and u. Which is fine. It's fine for because if you're already given f, then u doesn't matter.
Yes. Sorry. Yes. Yes. You're right. So that. Yeah. Yeah.
Maybe,
yeah. I think that. Yes, you're right.
Yeah. I don't know how to represent rapidly necessarily there.
Something like that.
Yeah,
yes. Yes. There's some. I'm assuming. Yes.
Absolutely.
Thanks, Susan.
Because f captures captures sort of everything, and u is some sort of like.
Yeah.
Summary, and if you're given everything plus the summary is the same as given.
Yeah, so absolutely. So yes, I shouldn't have drawn that line. You don't get to observe the fundamentals directly. You observe them only through y, which makes sense. Yeah. Yes.
And then we could actually average over, because that holds for any f. we can actually average over any distribution over F.
Yeah.
So we could just immediately plug in Q of F there instead of P of F given U.
Yes,
Being
but,
any distribution.
yes, and in fact we do that. So if you start doing tricks like that, where you choose different forms for P of F given U, you end up with what we call tilted variational Bayes. It's the same trick in another domain, and we actually add, we specify a Q distribution which depends on the data to ensure that the likelihood stays in there, and we think, we're hoping to sort of use that to damage EP. Now, in terms of how convergent, alternative to EP, which can be used for multiple likelihoods. Yes. So this trick is, we're doing a lot of stuff with this kind of trick, and you could put Q in. So I put P in because I want to illustrate that that you're minimizing this. But the sort of some of the tricks we get up to, and I think FITSI emerges, James and I have been talking about this, but you don't get a bound out of FITSI. FITSI kind of emerges if you put a bit of Y in on the side here. But the problem is you get some intractable terms, and then you have to throw them away, and you're not doing a bound anymore. And you can see that. You're actually doing, you've got one KL divergence term that can blow up when you do a FITSI in this case, which I think happens in practice, and you get bad results. That's sort of kind of part unpublished, part written. Yeah, so we're not really, as Zubin pointed out, that's kind of general, apart from I got this graph wrong. Apologies for that. So this is sort of saying, really, I like the idea of this being U, but you can't observe F directly, you observe it through Y. You can observe it directly if you make that deterministic link, but normally we don't think of that. Okay, so what happens now is that we can write down that I've written it this way in the notes, which, as I say, are on Y. P of Y given U is actually equal to some sort of P tilde of Y given U times exponential of KL. This is interesting because this KL over there. That's interesting. We don't normally think of things in that way, but it's very obvious when you think of things in this way that this can't be a probability distribution. So if you're doing something where this is a probability distribution and you plug that in to so you make an assumption about this, you just plug that in, then you get an approximation, not a bound. Because this is a lower bound on the probability distribution. Yeah? So this is that. But interestingly, when you look at the form it has, it's made up of a probability distribution of that form times some correction factors. So I'm going to call them Ci, and I'll write them down in a moment. But if you were to make this assumption, this is what people used to call the deterministic training conditional. And they made this assumption, and they then said, and Kyle and Joachim took this perspective that this was a model, that it was, the approximation was the model. One should just look at what you were saying about is your prior. And I think that was exactly what we think, and I had this argument with Michalis when he started working on this variational thing, saying, you know, I think that model perspective is really good, and it shows us why FITSI is the right thing to do, and these other things are wrong. You know, just think about what I think one point Joaquin had, dude, what's your prior? You know, look at what your prior is. Look at the approximation in terms of the prior. I think we're all very comfortable with that. But it's got some couple of weird effects if you assume that this is your prior. Because what happens now is you put a P of U over U, so you know what the P of U is. And then if you look at what this marginal prior is, which is what we sort of did in those days, when we could see that what we were getting was that the K was equal to this, and FITSI is similar, but KFU, KUU inverse KUF, which is this KFU transpose, plus sigma squared I. And then this was thought to be a very bad approximation, because if you think about this in terms of priors, it's very bad, because when you draw, so if we drew this for the sort of exponentiated quadratic covariance, the truth would be this. But what tends to happen, because you only get response in this low rank approximation if f is close to u, you get sort of things like that, that you're inducing variables, wherever your inducing variables are, you get high variance, and where they're not, you get low variance. And that would be a dumb prior. So people were anti-DTC. We didn't like it. Because FITSI actually replaced the diagonal on this and said, oh, let's put that in. But that's a wrong-headed view. That's not what's going on, because at norm of C, it ignores that actually what you're doing is maximizing a lower bound. And if the lower bound is tight, this effect doesn't happen. Because this term C is a brilliant term. C, when the Nicholas came out with this term, I was like stunned. I was like, that's the term we should have been minimizing. That's the term we were missing to get, because we would try and optimize the basis functions. When you see there is an approach with basis functions, U each has an input location. We were trying to optimize that, and that didn't work. Doesn't really work very well at all. Works better with FITC, but terribly with DTC. And I tried to come up with some penalties that could improve it, because what would happen is these basis functions move away from the data. It almost like gives up on the data, and that happens with FITC as well. But this penalty doesn't exist with FITC. What this penalty term is the trace, so it's the exponential of the trace. So I'm going to look at log C here. The trace of, so the half, so sigma squared KFF minus KFU, KUU minus 1, KUF. That is the posterior variance that you would see as if your data was U. So this here, we can draw what this is. So in our sort of plot of before, that's a draw from a Gaussian process. That was a joke. You've got a bunch of data here, and you're replacing them with U. So you've now got some observations U that you're putting in here, right? Now, what this says is if those were your observations U, you get certain error bars. And actually, it's based on the diagonal down here. And those error bars are the variance at the points where you've actually got training data. So this penalty becomes large, CI becomes large, if your inducing variables are sparse amongst your data. So what actually tended to happen is you get, where there's no inducing variables, you get very high variance. But the penalty is the sum of all these variances. And it's very important in getting the approximation, well, the bound right, getting better Gaussian process approximations. The sum of all those variances. And that, if that is 0, this trace term here, if you do predict posterior variance, you can show that you've recovered the actual optimal likelihood. Basically, if that's 0, this term here has no effect. It's e to this 0. And if it's e to the 0, then this has no effect. You know you've recovered as well as you would have done if you've seen the entire training data.
So you can actually compute that given a data set and the inducing points. So presumably you can actually find how bad your approximation is. So
yeah, at design time you can do it.
Why isn't it actually in use in any of the experiments that actually do GPVMs or sparse GPs?
That's why I'm here. I have no idea why people haven't woken up to this and are doing this more. We minimize over it very often, but it doesn't. There are problems with minimizing over anything like this in high-dimensional spaces. But you know, I thought that's a clustering algorithm as well, actually, in some sense. So what do we do in practice? We do things like k-means or k-means plus plus initialize. So the initialization for k-means, which is k-means plus plus, seems to work well in practice. But we do, it's in our objective functions. We deal with it. If you don't deal with it, you get very often very horrible results. And people say, oh, Fitzy, why would you do DTC? I was chairing a paper for LIPS where they were like, oh, this is all wrong because DTC is no good because of this point of view. But this point of view is actually fine. Have that point of view, but bear in mind you're not working with Gaussian processes anymore necessarily. You may be working with a Gaussian process, but you're not working with the same Gaussian process that you specified at the beginning. I think with Zubin's point, you know, oh, you're just introducing fixed basis functions. Fine, you look like you're introducing, you are if you do that. You're introducing a fixed basis function model with some fancy non-parametric stuff goes on. But it's still a fixed basis function.
So back to the question of if you can actually use that to assess approximation. You actually introduced this in the big data Gaussian process for big data, but you didn't actually use that. You did introduce it, but you didn't use that. You ran some experiments, but you didn't show we're this far away from the correct log marginality.
Didn't show what, sorry?
You didn't actually show that we're this far away from the correct log marginality. Our bound is that and that and that path.
Yeah, no, there's lots of things we can do to improve that paper. That's definitely not, I mean, I'm more and more thinking, when we write a workshop paper, a conference paper, we're trying to get an idea out there so that people talk about it. I'm not trying to say that's the definitive answer on that thing. In fact, I think for a community like ours, that's exciting. When people see it and say, oh, that's cool, let me do something with that. I mean, we've had so many ideas about that we could work on a subset, and we've got two choices. We could either lock that away and wait until we think we've done everything and then publish, and then say, aren't we brilliant? Or we could just throw it out there, and other people will have the same set of overlapping ideas with us, they'll work on it. But I think that those sort of ideas, not even that one necessarily, but these ideas for scaling probabilistic models for big data are too important to be hidden away in our lab while we try and finalise the best. I mean, we are still working on it, but I mean, absolutely, that's not the definitive answer on what we think goes on with those models. We don't have good ways of choosing the inducing locations in those cases, for example. We tried, I think James tried, and you need to ask him, but I think he tried doing sort of stochastic gradient descent on the locations of inducing variables, and it didn't work that well. But one of the sort of things you can see is, well, you could use different inducing variable sets according to where you are in the data. If you know, we can have thousands of inducing variables in that paper, because once you've got this formalism, the bit that's sort of the really clever bit, so this, what happens next, I should say, because we're over time already, what happens next is you put a prior over, so what happens next in the standard formalism for variational DTC is you integrate out u, because you've got this bound, you've got this approximation to log of p of y given u, and now in order to get the full thing, you just do the integral you meant to do in the first place. And that gives standard variational DTC. And to just give a perspective on what was going on, I think that we realized, or in particular James realized, I mean, we talk about this stuff an enormous amount, that that's a collapsed variational bound. So we had this paper on collapsed variational inference, and it's a way of sort of collapsing a bound. So you remove, you actually really have explicitly, you can always write it down, Q of U exists. But what you do, like in collapsed Gibbs sampling, is you marginalize out over U. You don't represent Q of U explicitly. And then I think what James noticed, he was talking with David Bly about these bounds and stochastic variational inference, is once you're back in that form, we're back in this sort of world that's quite close to parametric models, that we often have this situation. Not always, it depends on our factorization assumptions about, these factorizations match the ones between, that we have about y given f. But we're back to this world of what looks like a parametric model, that in a traditional sense, if we just had this, we would do stochastic variational inference to maximize the likelihood. Stochastic gradient descent. Robbins-Monroe optimization to maximize that likelihood for massive n. And once you've got your model in this form, boom, then you need to look at the sort of, how do you do the variational parameters? It's still a bound. You've got questions, it's still an objective that it factorizes over n. Some parts don't factorize, and that's sort of what, I've got all the authors written down. It's Paisley, Bly, Wang, Hoffman, I think. Is that everyone? Yep. Oh look, I've skipped way ahead without even looking at my notes. That's what they've sort of noticed and described ways of doing that with mini-batch updates and things like that. And that's vital, but you know, when I talk to Max Welling, he'd start saying to me, oh, anything you can do with stochastic variations we can do with funky, fine, cool, you know. I want it to be variational inference because I spent all my time understanding that, so I'm hoping, you know. But I absolutely admit that if there's really cool Markov chain Monte Carlo things of exploiting the same way and all the sort of things, Max, that's going to be brilliant too. And we're going to be in a whole new world of joy as we're all asked to be head of Facebook Labs. Google and everything else. So, but I would claim, I guess the summary point is, I think I have a little bit more, but yeah, so actually I'm on my summary thing now. Limited assumptions have been made about factorization a priori at design time. Yeah? So one thing that's going to happen if you get new measurements in, you might want to make some factorization assumptions as they come in about perhaps how y relates to f. You might want to make some design, and that's all right because you haven't seen y before, so you're allowed to do that. You might want to make some design choices about how you need to get, whether you need to get new inducing variables in to deal with this new. You might want to make some runtime choices about how you get these new inducing variables in. Oh, now I've got to get an inducing variable that gives me the integral of this function or some other thing in here. So, but you can do that at runtime, not design time. And it relies on real non-parametrics for the TT channel. So I have to be careful because, you know, it's that three-card trick. Where's the non-parametrics? We get to choose that the bandwidth of the TT channel at runtime, not design time. And these things are now variational parameters. All those bits are variational parameters. And they're really all over the model. I mean, all the models are sort of based on those. That's the sort of, I mean, there's some model parameters in that, but we can design a lot. KFU, we can say how these U's relate to the data. And sorry, I've overrun, but that was it.
So me and James started actually working on basically doing sparse GPs where the number of inducing points scales with the complexity. But not the complexity of the data, that's what you would want to have, but rather with the number of input data points. Instead of scaling that linearly with a number of points, which basically leads to a cubic runtime, you can decide, okay, let's impose a log, let's scale the number of points in a log linear way. Let's say that if we have n points, then we're going to have log n inducing points, and we're going to increase that very, very slowly. Yeah. And presumably that should allow you to capture more complex data under some situations. Although what you would want to have is basically scaling the inducing points, the number of inducing points with the complexity, and not with the number of data points. Because we did actually mention that several times where in justification for why you would want to use the non-parametric model by itself is that when you have more data, you would want a more complex behavior, which is often not the case. Often you have some very simple underlying function generating the data, and then just want to capture that, and you can just use, let's say, 10 inducing points, even if you have a billion points, observed points. But still, a good approximation to that in terms of time complexity would be to just use a low number of, a much smaller number of inducing points, and that basically still keeps it as a non-parametric model. So what did you actually have in mind for the inducing points? How do we, because you mentioned that several times.
I don't know, I think that's the thing I like about it, is I don't have to have anything in mind for it until I see the data.
You mentioned something about replicating behavior of the brain, about stored memory.
I mean, you know, I'm not saying that's just our excuse for getting the grant for doing that, because obviously brains have to do this somehow, and we want to work with these people. You have to do these collaborative grants. People don't fund us to do, you know, everything I'm describing now, we wanted to put in a program grant, we didn't get the program grant. So I would love to do just the methodology. I'm not prescribing, so you think, well, we're just using logarithmic, and I think that sounds eminently sensible, and that's going to work in some cases. But what I'm trying to point out is you don't even need to make that decision. You could start by doing that, and then see things went wrong. And you could even, in the stochastic variational inference, you could even switch on certain inducing inputs according to where you were in the, where that data point was in the domain. You could have heuristics that say, okay, these inducing inputs, they're so far away, they have no effect. So I'm just going to do something heuristic and say, pick up the nearby data, make the prediction with that. I mean, if you've got global covariance, it's difficult, but you could certainly use a heuristic to just update your inducing variables a little bit approximately. And we can get away with that. I mean, I'm not prescribing how you do these inducing inputs. Clearly this is the theory, but in practice, I don't know, however you like.
So, answering that, I think, that's right. Yeah, no,
I'm doing almost exactly the same thing. I try to combine your two papers, the Gaussian process for big data and variational inference. And I think I also have the same problem. Like it's very hard to run these inducing points. What I observed is that there's very strong coupling between the Q of U and the location of C. Like once you fix the U, then it's very hard to move C.
I think that's why it works hard with the stochastic variational inference, because like, moving things around for things that you've done before, you know, I don't think we've got pure answers on that, how one does that. Yeah, but yes, that's a challenge, isn't it?
Yeah, I was very curious. Like,
this is why I kind of wonder a bit, and I don't think we've tried this really, but just ignoring some of them, just leave them alone and bring in some others. You know, if you're in trouble in a regime, then hopefully it's because there's no inducing points nearby, so you could just put some there, and maybe have a heuristic for ignoring others. I don't know, or even a principal way of ignoring others. You could check, like, the trace terms for some subsamples.
So if you can't move them, just do some sort of, like, birth, death, or appear, disappear type trick where...
You kind of know, you could always regenerate them. Yeah, something like that. The thing about it is it doesn't matter, because all you're ever doing is reducing your lower bound on the variational likelihood. And since you're taking in a mini batch, one group at a time, you know, you only care about the tightness of that bound at the location you're looking when you do these stochastic approaches. So you could you can work with different parts of the model, yet what you're doing overall, I mean, I guess it relates to, you know, your stuff with Ed on these clusterings of data. You know, very often these inducing methods work less well than just fitting 5 Gaussian processes. Well, under this domain, you could kind of make those Gaussian processes sort of exist by setting up your inducing, perhaps, setting up your inducing points in such a way that they cause these things to cluster.
So this penalty.
Maybe we should...
Yeah, I'm worried that we're already now 20 minutes over.
Yeah. So,
lunch.
We'll let him have some lunch.
Yeah, so